Welcome everybody to a special edition N3AS seminar. Thanks everyone for joining us. And today we're very excited to hear from Jake Spisak from UCSD about constraints on axion-like particles from the CMB. So please go ahead, Jake.
Okay, yep. Thanks, Evan. And thanks for having me on. I think this is the first N3AS seminar I've ever given. So yeah, here at UCSD with George and Lukash, I work on sterile neutrinos, but I also work with Brian Keating, who I think I saw join the call, on some cosmic microwave background experiments. And so we recently had a paper posted to archive about an analysis I've worked on for a couple of years. And so that'll be the subject of this talk. The title of the paper is Constraints on Axion-like Polarization Oscillations in the Cosmic Microwave Background with POLARBEAR. Okay, so I'll start with the brief introductions to axions. And so the term kind of traditionally refers to the original QCD axion, which was proposed several decades ago as part of the solution to the strong CP problem. But here I'll be using a more generic definition of just a light pseudoscalar field phi. These are also sometimes called axion-like particles because they have similar properties, but just aren't really related to the strong CP problem. But I'll just call them axions. And so one area of motivation for this comes from string theory, which predicts that there should be several of these, several to hundreds of them, depending on the model, across a wide range of masses and coupling constants, or couplings to the standard model. This is sometimes called the axiverse. But here I'll be focusing on a kind of narrow mass range of interest, around 10 to the minus 20 to 10 to the minus 22 electron volts. So these are extremely light, and that allows them to act as fuzzy dark matter, which I'll talk about next slide. Oh, and I'll just say I'm happy with questions during the talk. I think somebody's monitoring the chat, so yeah, please interrupt me whenever you'd like. So the model I'll be talking about here is simple, just a basic mass term, and then a dimension 5 operator that has an electromagnetic coupling, with the coupling constant being G gamma phi. And so in principle, there are other couplings to the standard model. For example, the quarks, leptons, which have been probed in other experiments. But this coupling is really what we'll be targeting with this analysis. In addition, there can be higher order terms to the potential other than the phi squared term. But we'll be working in a regime where just the phi squared term is a good approximation. And so you can think about phi in terms of its cosmological evolution as just like a classical scalar field. And so the equation for its evolution in an expanding homogeneous universe is shown below. And in the range where the mass is much greater than the Hubble constant, you get simple sinusoidal oscillation. Also, the energy density contributed by the axion goes as the scale factor cubed. And so this allows the axion to be a dark matter candidate. So in particular, the ultralight nature of the mass range we're looking at means that the de Broglie wavelength of these particles are huge, like kiloparsec scales. And so a reason you might be interested in this is because of the potential to address kind of several issues known with cold dark matter at subgalactic scales. So in particular, these are the familiar problems of having too many small dark matter halos and the core cusp problem, where the density at the halo center is predicted to be too high. And the basic way that fuzzy dark matter addresses these is by kind of smoothing out structure or cutting off structure formation at the de Broglie wavelength scale. So if you look at the plot on the right, on the y-axis is the abundance of dark matter halos, and on the x-axis is wave number. And you can see what the predictions for the abundances are for cold dark matter versus fuzzy dark matter models at particular masses. Basically, fuzzy dark matter cuts off structure formation for these halos at a scale given by the de Broglie wavelength, thus solving the too many small halos problem. Furthermore, you can see that the predictions really agree kind of at scales larger than the de Broglie wavelengths, which allows you to recover, all of the successful predictions of lambda CDM with regards to structure formation. In kind of the similar way, the density at halo centers is smoothed out by the formation of solitons and fuzzy dark matter, thus resolving the core cusp problem. And so I should say that kind of the traditional solution to these cold dark matter issues is baryonic feedback. And so this is kind of an exotic alternative.
But Jake, I see we have a question from Susan.
I guess I will ask, it's a point of discussion whether or not cold dark matter has problems at small scales, but I don't think it's a definitive observational point that we have too many small halos. And I guess I just wanted to inject caution on that matter. I mean, I think it's a point of high interest, what actually happens to the cold dark matter paradigm at small scales. I think the most recent probes at small scales of cold dark matter comes from strong gravitational lensing. I'm certainly saying more than I know, but there's a group that studies that, or that claims that, what was it? Dark Matter Chills Out, I think is the title. It appeared in the last year or so. So I guess I wanted to just remark that it's very interesting to find axions, but I'm not sure there's necessarily small scale problems. Though there's been lots of controversy.
Sure. Yeah, and this isn't exactly my I wouldn't say I'm extremely well versed on the latest literature with regards to the too many small halos problem. I'm in particular, I haven't seen the dark matter chills out results. But yeah, it's certainly true that, I think depending on who you ask, there is or there isn't a problem.
So what is that? What is the observational statement in regards to too many small halos?
The observational statement is that cold dark matter predicts too many small halos relative to what we can observe simply, through galaxy counts. And I think also that the scaling as a function, like the number density as a function of halo mass, the scaling's incorrect. And so I think, the baryonic feedback explanation is that simply you just don't form baryons in these small halos because you can have like supernova explosions that blow them out. I'm not an expert on this, but that's kind of the problem statement. Okay,
so I want to say that I think there. Well, let me not detract you from the main issue, your talk. I would just like to say that the statement of too many small halos with respect to observation is something that can shift with time, particularly with improved sensitivity to, very faint objects. So let me just inject that thought and let you continue. Thank you.
Sure. Yeah, thanks. No, I agree that it's not. There's a lot of, I can think, room for less exotic resolutions to this statement. Okay, so kind of the focus of this analysis will actually be the coupling to the electromagnetic field. And in particular, the rotation of polarized light that it implies. So here the pseudoscalar nature of phi is critical. Because you essentially pick up a phase difference in plane waves that depends on the photon's helicity. So you can view this coupling simply as a modification to the standard Maxwell's equations. And if you make some approximations, like the field doesn't vary too much over the wavelength of light, you get a relatively simple modification. Here I show the modification to the electromagnetic vector potential in the red box in the bottom. And essentially, as the plane wave travels, you pick up a phase difference, which is proportional to the coupling constant divided by 2 times the difference between the axion field at emission and absorption. So that's delta phi. And this phase difference has different sign, plus or minus, depending on the photon helicity. So this is like a parity violating term, left and circular polarized light, have different phases. And the effect on linearly polarized light is to rotate it. So that's why this is sometimes called cosmic birefringence. And this effect has been known about for decades for the coupling of a pseudoscalar field to electromagnetism. And it's inspired a wide variety of literature that looks for this cosmic birefringence effect in various polarized astrophysical sources. So the source I'll be using or talking about today is the cosmic microwave background. And this is probably a very basic reminder for everybody, but I'll go through it. So as a reminder, the cosmic microwave background is a relic from the plasma of the early universe. And it was released several 100,000 years after the Big Bang, when electrons combined with protons to form hydrogen gas. We view it, so this is a relic of when the universe was extremely homogeneous. And so we view it today as an extremely isotropic 2.7 Kelvin black body. Furthermore, it has tiny ripples, tiny anisotropies, which give cosmologists a lot of information about perturbations in the early universe. So shown on the right is a sky map of these anisotropies. They're on the scale in temperature of tens to 100 microkelvin. And what we'll be interested in today is the polarization anisotropies. So the CMB picks up a very faint polarization signature due to Thomson scattering of the light on electrons. And the black lines on this map show the tiny linear polarization signature. And the scale of this is a few hundred nanokelvin. So if we turn to what the axion does to this polarization signature, it's actually a very simple observational signature. So if you recall, an axion, we can treat it just like an oscillating scalar field with some amplitude phi naught that in general depends on position and time, and some phase theta. And the oscillation period here we'll be talking about is set by the mass and is days to months for this analysis. And so I show again here the rotation of polarized light that comes about from this coupling. And if you think about what happens at emission and absorption, so the CMB is emitted over tens of thousands of years, which actually simplifies things because this means that many, many oscillation periods happen during this time. And the emission term is simply averaged out. Furthermore, the absorption term is due to the axion field at the telescope over a time scale of a couple of years that we do this experiment during. And so these length and time scales are much shorter than the axion field coherence length and time. That means that phi naught we can treat as fixed, and similarly the phase theta. And so the observational signature we're looking for is just a sinusoid with a constant amplitude. That amplitude is g phi naught over 2, and the angular frequency is just set by the mass. So now I'll talk a little bit, that was kind of the theoretical introduction. Now I'll talk a bit about the observations we use to look for this signature, which are from a telescope called POLARBEAR 1. So POLARBEAR was a CMB telescope located in the Atacama Desert in Chile, 5,000 meters above sea level. And it took data from 2012 to 2016 at a frequency of 150 gigahertz, which is the peak of the CMB spectrum, and 3.5 arc-minute resolution. So its primary goal was going after the B modes from inflation and gravitational lensing. But here we'll be kind of repurposing that data for this axion search. And the data we'll be using is from the first 2 years of observations, 2012 to 2014, during which time POLARBEAR observed 3 small patches on the sky. Those are shown in the sky map on the right. They're about 7 to 8 square degrees each, and they're located far away from the galactic plane to avoid dust and synchrotron emission foregrounds. The basic unit of time for this analysis is a single observation. which involves POLARBEAR staring at one patch and continuously scanning it for up to 8 hours, after which time the patch would set, and then it would go to a different patch, observe that for up to 8 hours, and kind of so on. And so over the course of 2 years, we got 515 total observations that we'll be using for this analysis. Okay, so to talk about how we extract the cosmic birefringence angle, I need to give a brief reminder about CMB power spectra. So a power spectrum, C sub L, involves correlating 2 points on the sky. And this is done by decomposing the sky in terms of spherical harmonics, which are indexed. One of the indexes is L, which corresponds to the angular scale. And because the CMB is statistically homogeneous and isotropic, this is really the way in which you extract the important information about the CMB. And so in the plot on the left, you can see various power spectra. So the temperature power spectrum is CMB-TT, which has been well measured now for over a decade. And its oscillations reveal information about oscillations in the early universe plasma. Similarly, the polarization power spectra, CMB-EE, is very well measured. And so here it's important to note that to decompose the 2 degrees of polarization, it's typical to use E mode and B mode patterns, which are shown here in the bottom right. The reason why you do this is because E modes are dominant in the CMB. They're the type that's produced during last scattering. And so this CMB-EE power spectra here reveals the faint polarization with the same types of oscillations that generate the temperature power spectra. The B modes are a very relevant science target for POLARBEAR and many other experiments for their ability to look at cosmic inflation. And so that's why a lot of these experiments are built. But that's not the topic of this analysis. We're kind of using that data for another purpose. And so fortunately, the EMB mode decomposition of polarization permits a really simple analysis of the rotation angle. So under a small rotation angle, oh, and I see there's a hand. I can pause here.
Oh, thank you. I just have a simple question. In principle, if I think of B modes, I can also generate them through late scale Faraday rotation from charged particles, et cetera, electrons. And I'm wondering, since is it just that the frequency of the light you're looking at is sufficiently high that the effect of Faraday rotation that goes like 1 over omega squared is therefore suppressed and negligible? Because it would, in fact, potentially contribute to your B mode signal. So I'm asking about conventional Faraday rotation from charged particles in the medium.
Yeah, so actually, Faraday rotation is used to search for cosmic birefringence from like primordial magnetic fields. Is that what you're thinking of?
That would be possible. I'm just saying this would have charged particles and would expect that the magnetic fields there as well. And I was just how to say, I'd remembered in B mode searches talking about numerical procedures or analysis procedures to scrub the data of late scale Faraday rotation effects. And I just wanted to remind you of that literature. It may not be relevant to your particular analysis because the frequency window you've chosen, but I'm not sure. I just wanted to make that comment.
Sure. Yeah, no, Faraday rotation, it is the same effect of this kind of cosmic birefringence. And in fact, POLARBEAR has published previous papers that look for primordial magnetic fields from this Faraday rotation.
Okay, I just wanted to point out in this regards to this analysis, there could be a plurality of physics interpretations. One would need to falsify to set a reasonable limit on axion, I guess, oscillations.
Sure.
Thank you.
Yeah, I think the key for this analysis relative to kind of other cosmic birefringence searches is the unique signature is really the sinusoidal oscillation that's totally coherent across the sky. So because it's due to the axion field. Oh, yeah, great.
Thank you.
So it is true that in principle, you could have that from other sources, but yeah.
No, you just defined for me why your research is unique. So I appreciate it. Thank
Sure.
you.
Sure, no problem. Yeah, so using the EMB mode decomposition of polarization, extracting a rotation angle is fairly simple. So the EMB modes essentially rotate into each other. And so here, using the small angle approximation, you can see that we've effectively applied a rotation matrix of angle 2 alpha. And we can exploit the fact that the CMB signature is E mode dominated to ignore the B modes and realize that the observed B mode signature picks up this small contribution from the E modes times 2 alpha. And so this B mode map really carries all the information that we care about. And so the way that you can look for this alpha is you correlate a single observation's B mode map with every other E mode map and form a CLEB power spectra. And by comparing that with the CLEE power spectra, which is known precisely, you can estimate a rotation angle alpha for each observation. So the way that's done kind of for one observation is shown on the right. So the CLEB observed power spectra is shown in blue. And the error bars here come from a bunch of noise simulations, signal and noise simulations that we have in the POLARBEAR pipeline. And by correlating it with the CLEE power spectra, you can extract a rotation angle, in this case, 0.74 degrees for this observation. And I should say we bin the power spectra here into 4 different multiple bins. So if you do this for all of the 515 observations, you get the time stream that's shown here. You can kind of clearly see the first season and the second season of data. And you can also see that, by eye, each individual point is noise dominated. And again, these error bars on the points come from simulations we have of the POLARBEAR pipeline. So to extract a sinusoidal signature, we'll be doing a simple likelihood analysis. Before talking about that, though, there is one minor wrinkle, which is that we extract a single angle for each observation averaged over the duration of the observation. And these observations can take anywhere from 4 to 8 hours. And so what this means is we're effectively averaging over the axion signal during this period, which limits our ability to probe smaller oscillation periods. For the frequency range we choose, in which our smallest period is a little over 2 days, this is a less than 3% effect. And so it's mostly negligible. So with this minor wrinkle, we then just have a simple chi-squared likelihood that we use to estimate the signal. We're estimating 3 parameters: the amplitude, frequency, and phase. And shown here on the right is just what an example signal would look like in simulated data. So here, I've injected a 5-degree signal, which is much, much larger than existing constraints and what we would expect. And which in our analysis would be a huge detection, just to show what it looks like. And so we do this analysis over a range of discrete frequencies from periods ranging from 50 days to a little over 2 days. And for the purposes of this news talk, I've put a couple slides in backup that talk a little bit more about the instrumental details of the analysis and why we restrict to this frequency range that I'm happy to talk about after. I'll just say too that this is kind of similar to like a discrete Fourier transform or some sort of periodogram that you would do to look for sinusoidal signals. In fact, in certain limits, the likelihood approach is identical, but the likelihood approach is just a little bit more flexible for our purposes. Okay, so now I'll go on to the results. So to test for a presence of a signal, we form a metric delta chi-squared, which is the difference between the chi-squared value with no signal and with our maximum likelihood fit to all three parameters. And the way we do this across all of the 1500 discrete frequencies is shown on the left. So for each of the frequencies, we find the maximum likelihood amplitude and phase for that frequency. And then we form this delta chi squared as a function of frequency f, and then pick the largest one. So you can see here, that's a delta chi squared of about 10.47 at a frequency just over 0.3 inverse days. We compare this value to a simulated distribution of delta chi squared values and to assess its significance, which is 1.7 sigma, which is a little high, but we claim no detection off that. And just to give you a sense of our sensitivity, our 5 sigma sensitivity is to sinusoid amplitudes of about 1.43 degrees. Okay, so now the last part of our results involve placing constraints on the axion-photon coupling constant. But this is a little bit tricky because we have to deal with the axion field at the telescope. So if you recall, the sinusoid amplitude is g gamma phi times phi naught over 2. And the basic problem is that we don't know the value of phi naught. So we know what its average value should be based on the local Milky Way dark matter density. That's this formula shown in the bottom here. But as I mentioned before, phi naught can vary in time and it has a typical coherence time, which depends on the mass. For the masses we have here, it's at least several thousand years. And so, in our 2-year experiment, we're basically observing phi naught that's fixed at some particular point in its kind of random walk through all these different values it can take. And so the probability distribution that governs its variation over many coherence times is a Rayleigh distribution. And so we need to, in effect, marginalize over this Rayleigh distribution in order to extract only the coupling constant. And so shown here on the right is just an example of what the variation of phi naught looks like over many coherence times. The inset here shows what it would look like for an experiment like ours, which is observing at essentially a fixed time. And so all you care about is the sinusoidal oscillation. But if you observed over, tens of thousands of years, then you would have to also average over this phi naught variation. Okay, so the way we deal with this is we marginalize over the unknown phi naught amplitude, and we place a 95% upper confidence limit on the coupling constant as a function of mass. And so the median upper limit we get is g gamma phi is less than 2.4 times 10 to the minus 11 inverse GeV. And it's dependent linearly on the mass, so that's at a mass of 10 to the minus 21 electron volts. And the basic reason why it's dependent on the mass is that in order to get the correct local dark matter density, you kind of have two levers, the mass of the axion and the value of the axion field. And so as you decrease the mass, you must have a larger field to compensate. And so what this constraint looks like is in the mass coupling parameter space as shown on the left. So the bound oscillates across all the 1500 frequencies we test, kind of in analogous behavior to what like a discrete Fourier transform would look like. And then we've drawn a median line through it as well. And so you can see right now that this analysis is not competitive yet with other ways that you can constrain the axion-photon coupling. So these other diagonal lines include other CMB experiments. This big green shaded area includes limits from actually the suppression of the polarization signature from averaging over the axion field when the CMB is released. So that actually suppresses the total amplitude of the polarization signature. This upper vertical or this upper horizontal line comes from the CAST experiment axion conversion from the sun. And these vertical lines come from limits on structure formation on kind of the smallest dark matter halos you can see. And so I'll note a couple things here about our constraint. The first is that we are not cosmic variance limited. So this green region actually is basically the best you can do given cosmic variance. But these constraints we're placing with this type of analysis are only limited by how well you can measure the polarization of the CMB. So future experiments like the Simon's Array or Simon's Observatory, which we're working on here at UCSD, should be able to push constraints down into this unexplored region. The second thing I'll note is that there are also a lot of constraints that I haven't shown here from other astrophysical sources, like protoplanetary disks, pulsars. But the advantage the CMB has is that the polarization signature is extremely well known theoretically and extremely well measured experimentally, and has no other known source of time dependence. So we expect that this signature should be kind of extremely clean from an astrophysical source perspective, which is not always true. And then furthermore, I'll note that we're the first CMB analysis of this type to incorporate the stochastic effect of the local axion field. So if you don't incorporate that effect, you get the dashed line shown here on the plot. So the stochastic effect actually worsens the constraints by a factor of a little over 2. Okay, so that's all I have. Just in conclusion, axions, which here we're talking about ultralight pseudoscalar fields, are a promising dark matter candidate. And they have a coupling to the electromagnetic field that can rotate linear polarization. And so we look for this effect in the cosmic microwave background via a sinusoidal oscillation in time. And so to do this, we use the POLARBEAR telescope, and we have a null result and use this to place constraints on the coupling constant versus axion mass. So thank you for listening. That's all I have.
Great. Thank you, Jake, for the very interesting talk. Do we have any questions for Jake? Please put your hand up virtually. So while we wait for people to chime in, I had a question just there on the last slide, Jake.
Yeah.
So you said that the difference. So for you, the red dash line is without the stochastic effect. So is that similar to the dashed lines for, say, BICEP and the South Pole Telescope? Is that, because you said that they didn't include that in their analysis. So what are the dashed lines for them indicating?
Oh, yeah. So the dashed lines are the constraints that they placed in their published results. The solid lines are if we kind of an approximation to allow one-to-one comparison, if we just elevate the constraints by the same factor that we get in the conversion from stochastic. But really the dashed lines are what they have published, and this is just an approximation. To really you would have to like redo the analysis to incorporate this.
Great, thank you. Now I see a hand from Evan Gross. Please go ahead.
Thanks, Jake. That was really interesting. So my question was almost, kind of just like some of the technical details. I mean, I'm getting, the impression, obviously, that what you would expect from the CMB should be pretty static, but, you're looking for this small variation in time. Are there things that you need to do to try and tease out, time variation, like the actual data that you get from a POLARBEAR, telescope? Does it have some time variation, due to just issues with the detectors or weather or anything like that you need to subtract out?
Yeah, so we do a series of null tests actually to kind of account for these potential sources. So some obvious things you can think of are like on year timescales, you might get seasonal variations. We don't probe those timescales, so we're fine. We did a systematic analysis to look for effects like issues with like imperfections in the beam, differential pointing, we do cuts on like the weather in our null test. So when there's high water vapor versus low water vapor. And so kind of passing the null tests and doing some more quantitative systematic checks are a validation there. I will say the biggest effect that we had was an issue with this half wave plate. So on the front of the telescope, in front of the lenses, we have a half wave plate, which rotates the polarization of incoming light. And it was placed there because it's fixed during an observation, but you can rotate it in 11.25 degree increments between observations in order to try to mitigate some of these systematics I talked about. And so they did this mitigation for the static analysis for their like main science goals. And so this can kind of like average over effects of always having the same attack angle of observation on the sky. It's a problem for us because it turns out that there's probably some inconsistency in exactly where the half wave plate was rotated to at the level of about half a degree for each step. And so because it was stepped between observations, sometimes at a cadence of like once every 3 days, sometimes they'd wait a month between it. This is actually a huge time-dependent systematic that's directly rotating the observed polarization signature. And so this caused a lot of noise at very low frequencies, which is why we truncate our analysis at a maximum period of 50 days. Otherwise, we would risk getting a false positive just from this half wave plate rotation. So that was kind of our dominant systematic.
Thanks.
Yeah.
Question from Susan next.
Yeah, so I just want to ask, what sets your constraint, your lower limit of your constraint to 10 to the minus 21 EV?
Oh, actually, the lower limit of our let's see here. The lower limit is actually about 2 times 10 to the minus 20 EV, and our upper limit is about. Oh yeah. Oh, sorry. Yes,
I meant the window you're constrained.
Yeah.
Because it can still be compatible with all the dark matter if it's in excess of 10 to the minus 22 EV. And so it's a point of interest to know if you can go lighter.
Yeah. So you mean like could we explore down here basically?
Yes.
Yeah. So that's really set by this half wave plate issue because we would need to go to longer periods. So future analyses, actually, there's 2 more years of data which don't have this half wave plate issue that would let us go down to longer periods. Eventually, you'll run into the fact that you get worsening constraining power once the oscillation periods you're looking for are like as long or longer than the total amount of data you have. But that limit would be around 2 years or so, which is significantly longer.
I don't have a feel for that. What would be the cutoff mass in that sense? I guess I'm not sure how small that would be.
Sure. Yeah. So it would be the mass is linearly related to the period. So, going from 50 days to like 700 days would be, what is that, like a factor of 14 or so. So it would be below 10 to the minus 22.
Okay, I think that's interesting because nothing requires this candidate to be all the dark matter. And so it might be interesting to set direct constraints in that ultra long wavelength regime. So.
Yeah, no, that's definitely true. And you can see that other experiments have gone a little bit lower than we have. Then you also start to run into some limits, some problems like once you get around a year, you start to worry about systematics from like seasonal variations or just, they make modifications to the telescope kind of on yearly timescales. But I definitely agree that theoretically, it's motivated. And also because of this kind of diagonal nature of the curve, you can probe lower coupling constants or smaller coupling constants.
Okay. Well, thank you very much.
Sure. Yeah, thanks.
I see a hand from Charles. Please go ahead.
Yeah, so I had a question. How might you do better and how much better might you be able to do?
Sure. So POLARBEAR stopped taking data. If we added the other 2 years of data, that's about 2 to 3 times the data volume. So you'd improve the constraints by a factor of √2 to √3. These other experiments, Spisak and SPT, have some more data to analyze. I don't know exactly the data volume, but I would expect with existing data, they could improve it by a factor of 2 or more. But really the way you're going to do better is with upcoming generations of experiments, like the Simons Observatory, for example. And it's been a while since I've checked the numbers, but I believe with the Simons Observatory constraints, projected constraints, you'll start to be able to probe into regions beyond this green washout area. Really the constraint is just linearly proportional to the error on how well you can measure the polarization angle of the CMB. And so the way to improve that, these experiments are kind of already optimal for observing the CMB polarization signature. So really the way you improve it is by simply adding more detectors, improving noise properties of your maps, which is going to be done in future generations of telescopes. But if I had to design a CMB experiment that to look for this effect, it would essentially look like existing experiments. Yeah.
Can you just take data more rapidly to go to higher frequencies?
Yeah, so to go to higher frequencies, you can, in principle, you can use existing data and just bin it in smaller time intervals. So, I didn't have to bin these up. It's very convenient for the analysis to bin everything into one observation, but I could try to take, in principle, arbitrarily small chunks of data and do the analysis. I think it's just, more difficult because then you have to worry about a single observation is nice because it's a consistent map of the patch from each observation. If you did it at smaller time intervals, you'd have to worry about like what sky area you cover at what points in time. And then you'd have to worry about all this filtering that's done at various levels of the pipeline. So it would just be a more complicated analysis. But yeah, in principle, you can go to arbitrarily small scales. I will say one thing that works against the motivation for doing that is the slope of this curve. So you would be going to higher mass or larger masses, but you get worse constraints on the coupling constant. So, in terms of where to spend the extra energy, going to lower masses is more beneficial.
Okay, do we have any more questions for Jake? I don't see any hands, so let's thank our speaker once again, and I will now stop the recording.